Good day, Bisons. I am here making our video notes. This is how you're going to be getting your notes from here on out. I do want to actually continue the chapter that we've been working on. You took the quiz right before you left. I would highly suggest that before you watch this video, you take a good 10-15 minutes and review your 8.1 through 8.4 notes, or 8.1 through 8.3 notes, my apologies. And refresh your mind about what we were talking about. Refresh your mind of arithmetic sequences and series. Refresh your mind of geometric sequences and series, because they are going to be used in 8.4 and 8.5. Okay, so let's get started. So in 8.3, we talked about finding the sums of finite geometric series. The series that have an end, the 20th term or the 50th term up to the 10th term, whatever the finite number was. 8.4 is about finding the sums of infinite geometric series. Yes, infinite meaning that they go on and 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 on. You get the point. So there is one catch to being able to find the infinite geometric series. Or the sum of infinite geometric series, and we'll talk about that catch in a quick moment. So that is our main goal. Our main goal is that you will be able to find the sums of infinite geometric series and then use the formula to help do some other thing that's pretty cool, actually. So just to remind ourselves, okay, we want to remember what a geometric sequence was. So a geometric sequence is any sequence that is of this form here, where we have a sub n is equal to a sub 1, that's our first term, times r, our common ratio, to the n minus 1 power, okay? So most of our sequences or series rules are going to be of this form. So the sum of an infinite geometric series with first term a sub 1 and common ratio r is found by doing the following formula. The sum s is equal to a sub 1, the first term, over 1 minus r. You'll notice that this is similar to the sum formula that we learned in 8.3, except now we don't have the top parentheses here. It's just a sub 1 over 1 minus r, okay? But here's the catch that I was talking about earlier. The catch is that this only works if the absolute value of your r, your common ratio, is a number that is less than 1, okay? So your absolute value r, your r needs to be a number of value that is less than 1. If it is anything bigger than 1, then the series does not have a sum. So that's what this is right here. If the absolute value of r is anything greater than or equal to 1, then the series has no sum at all. You can't add it up. Okay, the whole reason that we want r to be less than 1 is because the number keeps getting smaller and smaller and smaller if your ratio is less than 1. Like, think of the number like the half. If your ratio is half, then you're just cutting something in half over and over and over again. So 2 cut in half is 1, and 1 cut in half is a half, and a half cut in half is a quarter, and a quarter cut in a half is like 0.125, and so on and so forth. They're getting smaller and smaller and smaller. That you can actually come to like an asymptotic sum. When if our ratio is bigger than 1, that means our numbers are getting bigger and bigger and bigger and bigger, and therefore we won't be able to actually get a sum. Okay, so we want to make sure that we pay attention to the r. So the first thing we want to do when we're trying to find the sum of an infinite geometric series is to pay attention to the r and remember to check the r, okay? So we have a series here. We have the summation of I equals 1 to infinity, so infinite, okay? Of this rule here, we have 3 times 0.7 to the I minus 1 Okay, so remembering that this is our geometric series and the form of our geometric sequences here, a sub 1 times r in our parentheses raised to the n minus 1. We want to check the r, okay, our common ratio. So our ratio here is 0.7. And so we do the absolute value of 0.7. That is actually, in fact, less than 1. So we are good to go and move forward to use our formula. So we have our sum is equal to, we need a sub 1 and we need the ratio. So we know that our ratio is 0.7. A sub 1 is our first term right here. So we can identify those as a sub 1 equals 3 and r equals 0.7. And so we just start plugging in. Our a sub 1 goes on top here. That's our 3. And then, of course, we have our 1 minus our r, which is 0.7. Okay. And so this simplifies to 3 divided by 0.3. That worked out nicely. And actually dividing that, we get that our sum is equal to 100. So all of this will eventually add up to 100. Cool. And that's it. That's our sum for this geometric series as it approaches infinity. Okay. Sometimes we're not given summation notation like this. We're given a actual list for a series, which actually means that we have to now figure out the ratio, the common ratio here. And I hope you remember how to do that. We take the next term divided by the first term to find the r. Once we find the r, then we got to check it. Okay, so 3 divided by 1. Okay, and we get a 3. And then we're going to do 9 divided by 3. We also get 3, and so on and so forth. Okay, our a sub 1 is actually 1. We can identify that straight from the series. But then check the r. Okay, so we need to make sure we actually compare the r to 1. And notice that if I take 3 and I do the absolute value of it, I mean, either way, you'll notice 3 is greater than 1, which means we look back up here. If r is greater than or equal to 1, then the series has no sum. Therefore, this series has no sum because r was greater than 1. Okay. Now I want you guys to go ahead and try it with these two. We have one in summation notation and one as a list of the series. Pause the video, go ahead and complete these two problems to the best of your ability. Okay, here are the answers that you should get to. And once you have checked your answers, I do want you guys to go ahead and look at the work and compare the work. Okay, hopefully you tried this on your own before you actually write down this work. Okay. Now, moving on to our next example here. We have a word problem, okay, and it is about a pendulum. So if you don't know what a pendulum is something that swings back and forth, okay? So think of a necklace with like a pendant on it. And if you were to hold the necklace at the top with your hand and let it hang, and then just grab it and release it on one side and just let it swing back and forth, that would be a pendulum. So we have a word problem here. It says a pendulum that is released to swing freely travels 18 inches on the first swing. On each successive swing, the pendulum travels 80% of the distance of the previous swing. What is the total distance the pendulum swings? So it starts off, the first swing is 18 inches, but then every other swing, every next swing, it's going 80% of its previous swing. So the second swing is 80% of the first one. The third swing is 80% of the second one. The fourth swing is 80% of the third one. So it would look something along the lines of this. So if we have a pendulum here, and I started on this side, and I let it swing over, that swings 18 inches on the first swing. So the next swing coming back, okay, would essentially be something like this, where we have 80% of whatever 18 inches is, because that was the first swing. So I would essentially be able to get that by doing 18 inches on the first swing times 0.8, representing our 80% in decimal form. So second swing would be whatever 18 inches times 0.8 is. And then the third swing, going back, is now 80% of whatever the second swing is here. Okay, so if I have 80% of the second swing, well, the second swing, oops, my bad. The second swing is 18 times 0.8. So this would be 18 times 0.8 from here times another 0.8 to get this one, which is essentially 18 times 0.8 squared. And we can continue with this to the nth swing, where at the nth swing, we get 18 times 0.8 to the n minus 1, because we have all these other swings before we get to the nth swing. Notice this looks a lot like a geometric sequence. Here's my a sub 1, 18 from that first swing. My rate of my common ratio here is 0.8 because it's decreasing, okay, to 80% each time. And so I can go ahead, it says, what is the total distance the pendulum swings? Total usually means sum, add up. So I go ahead and I do my sum here, using my 18 inches as my a sub 1 and my 0.8 as my rate. Now 0.8 we can tell is less than 1. So I have 18 divided by 0.2 here, and I get that the sum is 90 inches. So word problem deserves a word answer. The total distance the pendulum swings is 90 inches. Yeah, I highly suggest you pause and rewind this and maybe re-listen to it again, just to better understand it a little bit. Okay. Moving on to the next cool thing that we can actually do with the sum formula of a geometric series. Okay, so if we take a look here, it's very offbeat here. It says write 0.242424, and if this dot 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 means it would literally continue 242424242424 as a fraction in simplest form. Okay. So I want to write this as a fraction in simplest form. Notice this is a repeating decimal, and you want to pay attention to how often it's repeating. This decimal particularly is repeating every two numbers, 242424. So the steps on how to actually write this as a fraction in simplest form is the first thing you do is you rewrite this decimal as a series. So you take each repeating number, so 0.24, that's the first set of repeat, plus 0.00, the first 00 takes up these first two numbers, and then the repeat of the numbers, 24. So 0.24 plus 0.0024. If you want to add that in a calculator and see that you'll get 0.2424, check that yourselves. Plus 0. Now notice this time I'm putting 4 zeros to represent these guys here, 0.000024, and so on. And I would continue. The next one would be 0.00000024. So you write it as a series when you're adding the repeating numbers. Okay. The next thing you want to do is you want to take that and you want to find a common ratio. So using this series here, find your common ratio. So you take the next term divided by the previous, 0.0024 divided by 0.24, and that gives you 0.01. Using the common ratio and your first term, you now take the sum formula for infinite geometric series, and you find your you use your a sub 1, 0.24, divided by 1 minus your common ratio, 0.01. And we just go through and we simplify this. So this becomes 0.24 divided by 0.99. Each of these have two decimal places, which means if I multiply them each by 100, I will get, I will be able to move those decimals over essentially. And so I get 24 over 99. And then the goal is, obviously it's a simplest form, so the goal is to simplify that as much as possible. They're each divisible by 3. And so by dividing top and bottom by 3, I get 8 over 33. If you want to double check it, go ahead, put 8 over 33 in a calculator, and you'll see that you get 0.242424242424.